Hey y'all, welcome. Yeah, so this is a really exciting video, as you'll see in a little bit. And here what we're doing is the integral of 1 over z. And yeah, it will come in two parts, part A and part B. But first, I'd like to say that you need to watch these videos on complex integrals in order. I ordered them in a very specific way. And unless you have your own background knowledge, watching them out of order will mean that you'll struggle to understand some of the videos, yeah? All right, okay. So let's commence with part A, where we have to contend with figuring out the value of this integral on any simple closed contour C not enclosing the origin. And here's one possible visual of a simple closed contour C not enclosing the origin. Of course, there are infinitely many possibilities, but here's one possible visual. And notice where the arrow is going. It's going counterclockwise, so as to be positively oriented, right? Okay, all right. Now, we know from the end of the video on the evaluation theorem and that corollary that given that a function f of z is analytic in a domain D, then the value of the integral on any closed contour in that domain D is equal to 0. Now, notice that 1 over z is analytic everywhere except for z is equal to 0. And for a complex valued function, where it's not analytic, we say is a singular point. So the only singular point for the function f of z is equal to 1 over z is equal to 0. And since we've avoided that in part A here, because we're dealing with a simple closed contour not enclosing the origin, and therefore avoiding z equals 0, since we're avoiding z equal to 0, we see that by that corollary at the end of the video on the evaluation theorem, this integral is going to equal 0, right? Okay, all right, and we don't have to labor more to, show that this integral is equal to 0 over this contour C. Okay, and in fact, it's equal to 0 for any contour C not enclosing the origin, right? And that's the point of part A. Okay, we're done with part A, and this was quick, but part B will be a lot more work and therefore more fun. All right, so the fun begins. And here in part B, we're still doing the same integral as before, but this time over any simple closed contour C enclosing the origin. So where do we start? Well, how about this visual? Now, before we do anything else, let me explain this visual. Okay, now, this red contour is made of C1, which is most of it, right? And then this little bit L1 to go inside, and then this small circle centered at the origin that we could loop around, and then this little bit to come back out onto C1. So this red contour, which we're going to call C, is made of C1, L1, C2, and L2, right? Those guys together make this closed contour C, which avoids the origin, yeah? All right, so the idea is this. We want a simple closed contour that encloses the origin. That's C1. That's to say that, pretend for a second that L1 isn't there, C2 isn't there, and L2 isn't there, and this gap is not there. So then C1 would be exactly as we require here in part B. It would be a simple closed contour enclosing the origin. So we start with C1 being a simple closed contour that encloses the origin and doesn't have this gap, and then we make a cut. It doesn't have to be here. We make a cut anywhere, and we make a cut so as to use something like L1 to go in, and then we use something like C2 to have a small circle around the origin to loop around, and then we use something like L2 to come back out onto C1. And this idea, this cut that we make, is actually called a crosscut. And this idea of a crosscut plays prominently in later videos on complex integration. So it's something that you really need to understand. And if you don't understand it by the end of this video, then you should ask me questions in the comment section, and I'll be happy to explain. But yeah, basically, I'm going to repeat myself one more time intentionally. We start with C1 being a closed contour that encloses the origin, and then we make a crosscut to go in and then loop around a small circle and come back out and that way we avoid our singular point. Remember, 1 over z is analytic everywhere except for z is equal to 0. Its singular point is z is equal to 0. And using this crosscut, we avoid that singular point, yeah? All right, now, as I've said, we're going to call this red contour made of these 4 guys, we're going to call it C. And so then C would be C1, right? And then plus L1, and then minus C2. I'll explain why it's minus C2, and then plus L2, and that's all of it, right? That's C, and that would be this red contour, right? Now, you should know why it's minus C2, but remember, we have to be positively oriented, meaning we have to move in a counterclockwise direction. That means that in order for us to keep C positively oriented, we have to loop around the small circle C2 in this fashion, but that's clockwise, right? And therefore, it's going to be minus C2 because this arrow has C2 going clockwise to keep C positively oriented. Yeah? Okay, all right. So that's why we have the minus sign in front of C2. Okay. And clearly, the integral over C, right? The integral over the closed contour C is going to be the sum of the integrals over these 4 contours, right? Okay, cool. Now, we know from part A that since the contour C has a region enclosed where 1 over z is analytic everywhere in that region, as we have avoided that one singular point, right? Inside of the contour C here, 1 over z is analytic, right? Because, again, we've avoided that origin, which is the only place where 1 over z is not analytic. It's only singular point, right? Okay, and therefore, the integral over c of 1 over z is going to be 0 from part A, right? But then also, what we do is we take the limit as the radius of this small circle around the origin, C2, goes to 0. So the limit as the radius of this smaller circle, C2, goes to 0, would have the gap here on the crosscut also go to 0, right? Meaning that L1 and L2 will be of equal length, but in opposite directions. And therefore, the contribution from the integral of L1 plus the integral of L2 to the integral of C is going to be 0. So first, we know the integral over the contour C is equal to 0, but we also know the sum of the integrals over the contours L1 and L2 is going to be 0. And that's because, again, as the radius of this smaller circle C2 goes to 0, the crosscut gap goes to 0, meaning L1 and L2 will have the same length, but they're oppositely oriented so as to keep C positively oriented, right? And so the sum of the integrals over L1 and the integral over L2 is going to be 0, meaning that the integral over C, which is equal to 0, is just going to reduce to the integral over C1 minus the integral over C2. And so let's show that. So I've already explained sufficiently why the integral over C has to be equal to 0, and that's from part A. And I've already explained sufficiently why the sum of the integrals over these two contours, L1 and L2, has to be 0. And therefore, clearly, the integral over C is going to equal just simply the integral over C1 plus the integral over C2. But I also already explained why we have to have this minus sign for in front of the integral over C2, right? All right, cool. Now, this here, the integral over C being equal to 0, means this is equal to 0. But then if this is equal to 0, it means that the integral over C1 is equal to the integral over C2. Oh, how nice. Because that means that in order for us to do the integral over C1, we could just simply do the integral over C2, which is a small circle centered at the origin. Okay, but a small circle centered at the origin can be defined as r times e to the I theta. So we could just make z equal to r times e to the I theta, right? And that way, 1 over z will become, 1 over z will become 1 over r e to the I theta, which, if we use exponent rules, will turn into this. And I said and didn't have anything to say like a second ago because, well, I was just going to say and, like we've seen this idea of using z equaling r e to the I theta in the previous example on the integral of z. It was just that there we knew that the circle was of radius 1, so r was 1. But here we don't know the size of this small circle, c2, right? So we use r, right? We keep the r. Okay. But yeah, it's clear why 1 over z has got to look like this. And based on z being r e to the I theta, dz will clearly be equal to I times r times e to the I theta d theta, right? And so then our integral, right, will become this, right? Again, the integral over c1 is the same as the integral over c2. That's why we were able to go in this direction, right? Okay, and also because theta is going on this circle, right? It goes from 0 to 2 pi, right? And so that's clear, and I've done that before in a previous video or previous videos, perhaps. So you can watch those. But yeah, now inside of this integrand, or on the integrand, inside of the integral on the integrand, sorry guys, we have some conveniences. R to the minus 1 and r, right? That's r to the 0, which is 1. And then e to the minus I theta and e to the I theta, that's e to the 0, that's 1. So this integrand simplifies just to I times d theta. How nice. Because then we can factor out the I, right? We can factor out the I and just do the integral from 0 to 2 pi of d theta. And clearly the integral from 0 to 2 pi of d theta is 2 pi. And so the answer is 2 pi I. Isn't that really cool? I thought so. And by the way, this number 2 pi I will come up pretty frequently when you're doing complex integration. And additionally, like the idea that like 1 over z turns into having this integral will also feature prominently in future videos, including the next one I'll make. The next one I'll make will be the integral of z to the n, where n is an integer, and therefore when n is -1, it will include this video, because when n is -1 on z to the n, we get 1 over z, right? And it will also include the previous video, because when n is equal to 1, z to the n just becomes z, right? So we're going to state a more general result of the integral of z to the n in the next video, which is why I ordered my videos in the way I did. I told you should watch them in order. All right. I hope you enjoyed this, and yeah, keep watching. Take care.